on HS diagram how the expansion will take place, then the classification of the steam turbines, and then we look into what do you mean by a compounding of steam turbines, in that pressure compounding, velocity compounding, and pressure velocity compounding. So further, we have to look at the expressions for work done for both single stage impulse as well as the reaction turbines. Let's look one by one. So that we call it as analysis of single stage steam turbine. So I have taken an example of derivation turbine. There, the amount of energy that is getting converted is complete kinetic energy. I don't have any kind of pressure energy left over there or static energy left over there. And one more peculiarity of this particular D-level turbine is all my blade angles are same. What do you mean by it actually? It is like I have been telling you that in impulse machine, they're almost like a curved casing. We have seen your Pelton wheel, no? So maybe half of that Pelton wheel, it may be very similar to that. Then I do have where the majority of the expansion of the nozzles means the velocity is going to increase to a very high value. And then you may be having a rotor. So I'm getting a single stage. That means a single stage, I do have one set of a nozzle and one set of rotor. Okay. Then when you look at the rotor, the kinetic energy is getting absorbed. Kinetic energy is getting absorbed, so that it is called as expansion that takes place in the nozzle. The same pressure, so the P is almost constant in an impulse machine. Okay. Now, so there is some velocity triangle which is given. But I want to draw and show you how this velocity is for the combined velocity triangle. Okay. Combined velocity triangle for, so if one as inlet, and two as outlet. Okay. What is one actually? One is nothing but your low pressure side or your water where the fluid enters. And two is nothing but where it's a low pressure side where your fluid will exit. Now suppose the fluid is entering, so it's a common velocity, that is your U. U will common. U will be a common thing. And I have been telling you that the fluid will be pushing your rotor in case of a turbine. In case of a compressor or a pump, the rotor will be pushing your fluid. So sign convention, if you go back and see in Euler equation what I have done, so if it is from I have taken for a pump compressor and for right to left for a turbine. So I go by same sign convention. This is my U. So this is U, which is from right to left. Okay. Now, as this particular velocity, the velocity or velocity will be coming into it, actually, I can draw a combined velocity something. So this will be my V1. That is the absolute velocity which is entering. Okay. Then I'll be having your VR. So the VR will be something like. So I can construct a velocity triangle like this is my VR1. So there are two components of your velocity V1. So one being your VW1, one being F1. Okay. So this will be my VW1, which is in this direction, and I will be having V1 in this direction. Then if I try to put the angles actually, so this will be my alpha, that is a flow angle, and this will be my blade angle beta 1. So as I told, your beta 1 and beta 2, a line, okay, I can draw a line with beta 1 is equal to beta 2 like this. Okay, I can draw a line with beta 1 is equal to beta 2 from this particular thing. So what it is actually, this is my VR2, that is my VR2, maybe I'll light a little, VR1 is equal to VR2 here, so slightly, okay, and then I can complete it my, so I have your EF1. I'm drawing now, not drawing to the scale, so that's why I'm getting this. If I draw to the scale, I'll be getting a neat velocity triangle. Okay, this will be my VF2, and this will be my VW2. So I have written all the directions. So this will be my alpha 2, this will be my beta 2. Okay, now if you look at it closely, if I try to name the triangles with, if I call this as A, okay, this as B, this as C, this as D, okay, then this as E, and this point as F. Okay, I just named it actually. Now if from this velocity triangle, let me write some few points actually. What is it actually? If you take AD, what is AD? AD is equal to this particular thing. I call this as X or AD is equal to VW1 minus your U. See, this will be very good when you are trying to analyze your velocity triangle using your trigonometric principles. Then what is your AF? Okay, AF actually this particular thing. If you try to take this AF, okay, what it will be actually? That will be your VW2 plus U. So if I take AF, this will be VW2 plus U, and for this condition, beta 1 and beta 2 are same for this particular D level condition. This is how you can write your velocity. This is one way of writing your velocity triangle, which is right. I have seen some of the textbooks, what they take actually, they try to take the velocity triangle with this. So with the top they are going to put. So at the top they will put the U, okay, fine. They are going to put the velocity V at the top, and they are going to put the V1 like this. This is the direction of your V1. Then this will be your VR1. Okay, this will be my VR1. Okay, so that this is my beta 1. Sorry, VF1. This is my VF1. This is my VF1. Okay, this is my VF1, and this is my VW1. So with the direction, this direction, and this will be by beta 1, alpha 1, fine. Then I can go and write this VR2 like this. VR2, this will be my VR2. This is VR2, and beta 2, beta 1 equal to beta 2 for this condition. I V2, this will be like this. This will be my V2. Then I can close with your VF2. And close with your VF2. Then I have my VW2. So this is my VF2. Then this is my VW2. Then this is my alpha 2. So both the triangles are correct. Okay, either I can draw the velocity triangle like this in the top what I have shown, or I can draw like this. So both the combined velocity triangles are same. See, few textbooks try to follow, if I call this as A, few textbooks will try to follow B. So should not be confusion in the one particular thing. What is very important is your vector addition and subtraction. So those things, if you are able to satisfy, then your velocity triangles will be perfect. Okay. Now, once we have drawn this particular thing, now let us look for the expression for the done. Okay, expression for the work done. Expression for the work done. Expression for the work done. Now I will try to take this particular velocity triangle. So, okay, same velocity triangle if I try to take. Now, what is it actually we have from, say, one is the inlet velocity triangle. So if I try to, so all V1, VR1, VF1, VW1, they belong to your inlet velocity triangle. That means I can call that as one is your inlet, two is your outlet or exit velocity triangle. Okay, this we have. Now, already we have got the expression for work done from Euler expression. So we have the work done expression. We have the work done expression from Euler equation, which already we have derived from the Euler equation. What it is actually, your W is equal to VW1 minus VW2 into U. Why it is U here? Why it is U here? Because this is an axial flow machine or a combined velocity triangle, axial flow machines. Your U's are same. Your U1 and U2 both are same. In most of the steam turbines, they are all axial flow machines are used. So here U1 is equal to U2. This is particular. Otherwise, what I would have written, V1 into U1 minus VW2 into U2. I would have written it. Now, look at it here. Now, VW1 is in which direction? VW1, this is the direction for your VW1. Look at this here. Now, what is the direction of your VW2? Your VW2 is in this direction. So now, as VW1 and VW2, they are in opposite direction. Okay, VW1 and VW2 are in opposite direction. This quantity will become minus of minus. So this expression will automatically become VW1 minus of minus VW2 into U, because minus VW2, which is in opposite direction. So this you have to consider, and you call this as equation number 1. Okay. Now let us try to look at the inlet velocity triangle. If you look at the inlet velocity triangle and use our trigonometric principles, what is your cos beta 1? Cos beta 1 is equal to, if I call this as x. Okay. Cos beta 1 is equal to your adjacent side divided by your hypotenuse, that is VR1. So x by VR1. What is x actually? It is VW1 minus U. What is your VW1? VW1 is your V1 cos alpha, because you would say it's your adjacent or tangential component of. Okay, so that I'm going to write. So what I can, so from the inlet velocity triangle, I have cos beta 1 is equal to, that is x by VR1, or I can write cos beta 1 is equal to, what is your x actually? It is VW1 minus U divided by VR1. Okay, so this, if I call it as equation number 2. Now I go back here. What is cos alpha 1? So if I take, consider the same inlet triangle, what is cos alpha 1? Cos alpha 1 is equal to your, so this particular thing, it is equal to VW1 divided by V1. So I can write, so from the same thing, cos alpha 1 is equal to VW1 divided by V1, or I can write VW1 is equal to V1 cos alpha 1. So what I'm going to do actually, I'm going to substitute for VW1 in equation 2. So substitute for VW1. Substitute for VW1 in equation 2. What I'm going to get then? I'm going to get your cos beta 1 is equal to V1 cos alpha 1 minus U divided by VR1. So I already have said, if I call this as, let me call this as equation 2. Okay, let me call this as equation 3. So this is 2, 1, this is 3. So this is about your inlet velocity triangle. Or if you want, I can simplify. I can simplify this as, see, I can write this as VW1 is equal to V1 cos alpha 1, or I can write your VW1 itself. So if I take only this quantity, if I take only this quantity, if I take only this quantity, I can write VW1 is equal to your U plus VR1 cos beta 1. So that also I can write. Either substitute for your V1 cos alpha, or you can write it as VW2 U plus VR cos. I write what I want. Okay. Consider the exit velocity triangle or the outlet velocity triangle. From the outlet or exit velocity triangle. Let's come over here. What is actually cos beta 2? Cos beta 2 is equal to, we call it as maybe U plus E. It is U plus E, VW2 plus U. If I call this as Y, let me call this as Y. Okay, let's call this as Y. This is Y. Okay, what is this Y actually? It is VW plus U. So it is cos beta 2 is equal to VW2 plus U divided by VR2, or VW2 is equal to VR2 cos beta 2 minus U. I can write it. So from the exit velocity triangle, I can write cos beta 2 is equal to your Y, that is Y divided by VR2, or I can write it as cos beta 2 is equal to VW2 plus U divided by VR2, or I can write VW2 is equal to your VR2 cos beta 2 minus U. I am called that as equation number 4. So what is your VW1? So VW1 is equal to U plus VR1 cos beta 1. And what is my VW2? VW2 is equal to VR2 cos beta. So I have these expressions and will try to substitute in my main equation. Okay, I will try to substitute this in your main equation. So if I substitute what I'm going to actually, I can simplify my equation 1. So this is one part I can write. Okay, substitute the values of VW1 and VW2 in equation 1. What is VW1? VW1 is equal to U plus VR1 into cos beta, VR1 cos beta 1 plus U. Then VW2 is equal to VR2 cos beta 2 minus U. So this equation I am going to substitute in my equation 1. So what will happen? Your W is equal to U plus VR1 cos beta 1, okay, plus, that is for VW1. Then for VW2 it is VR2 cos beta 2 minus U. Then I have U outside. So this is the expression for your work done. Now I will try to open the bracket. So inside, if I try to open the bracket, then I try to multiply. So inside, if I try to open the bracket, it will be U plus VR1 cos beta 1 plus VR2 cos beta 2 minus U. Okay, then multiply by. So plus U, they just simply cancel out. I am left with U. Okay, I am left with, let me take U in the front. So U into VR1 cos beta 1 plus VR2 into cos beta 2. This is the expression what I have. Now what I am going to take? I am going to take VR1 cos beta 1 outside. If I take that, so this equation can be simplified. I can simplify this by taking U into VR1 cos beta 1. If I take it out, this will be 1 plus VR2 into cos beta 2 divided by VR1 cos beta 1. So let me call this as equation number 5. So now look at this actually. So this is a very general expression what I have. Now I told that for a kind of maybe a D-level turbine or any kind of impulse turbine, I can generalize this expression. What it is, so if I take for example some CB or something, so let me call CB is equal to VR2 by VR1, okay, or some K is equal to beta 2 by cos beta 1. So cos beta 2 by cos beta 1. So now I told that for a D-level turbine, for a particular impulse case D-level turbine, you have other impulse machines also. I am trying to get an work done expression for a generalized one. Suppose, but for a D-level turbine, what will happen? Your CD will be 1, your K will be, so cos beta 2 and cos both are same. Your VR2 and VR are same. The expression will change. So equation 5 will change. So I can write this particular expression as, okay, more generalized form I can write it as W is equal to U into VR1 into cos beta 1 into 1 plus CB into K. Okay. Now, what is this VR1 cos beta 1? Okay. If you go and look at the equation number 3, see VR1 cos beta 1, I can write it as V1 cos alpha 1 minus U. See this expression I can use. So VR1 cos beta 1 is equal to V1 cos alpha 1 minus U. So from equation 3, substitute for, from equation 3, substitute for VR1 cos beta 1. If I substitute, what will happen to your W? Your W is equal to U into V1 cos alpha 1 minus U into 1 plus CB into K. Okay, so I can call this as equation number 6. See now, if you look at it actually, now here, what are the typical things? For a given value of alpha and speed, so what is speed actually? That is U. For a given value of alpha, that is your flow angle. For a given speed, your CD, that is your VR2 by VR1, or your blade angles, I can maximize. That means your work depends on, your W depends on these parameters. For, see, if I keep my alpha, constant, okay, or if I keep my U speed constant, or I can keep my, your relative velocity, if I keep my beta constant, automatically your relative velocity will become constant. So how can maximize it? That means for this condition, so for a given value of, your flow angle alpha 1, speed, that is En, which is directly dependent on your U, so U depends on your N, that is pi dN by 60. Then your blade angle, which is having an impact on your CV. Maximize the work done. How can I maximize my work done actually? So you can maximize also this particular thing. See, if I do that, this particular equation, see what I can do, a maximization of this particular thing, your dW by du, that means it depends on your speed. So it depends on your speed. So what I can do to maximize my work, to maximize the work done, because those blades and your alpha, those things I can keep it constant. So your work done becomes directly a function of your u. So if you want to maximize my work, actually what I will do, I will take this equation 6, that is your dw by du, and equate it to say 0. If you want to do that, so what I am going to do, anyway, this quantity is automatically, this will become 0 if I take it to the left hand side. So this equation I can write it as, okay, d by du into only this particular thing. So u into, this will be u into v1 into cos alpha 1 minus, it will be u square. So other quantity will become to the 0, so that if I take it to the denominator, this is the equation what I am going to do. So this equation I will differentiate it. So d by du is equal to, I am going to get v1 cos alpha 1 minus, if I differentiate that particular, I am going to get 2u is equal to 0, or I can write v1 cos alpha 1 is equal to 2u, or I can write u is equal to v1 cos alpha 1 by 2. So let me call this as expression number 7. So for a maximum value, or if you want to get the maximum work done, your u will be equal to v1 cos alpha 1 by 2. So substitute this value of this particular, so substitute the value of u in my equation 6. So substitute the value of equation 6, we are getting my, okay, so I will be getting the expression for the maximum I am going to do. So if you get that, substitute the value of u in equation 7, equation 6, in equation 6. Okay, if I do that, what I want to get? So W max is equal to, wherever u is there, so u is equal to cos alpha 1 by 2. So I can write v1 cos alpha 1 by 2, okay, into u is there. I can write, so already v1 cos alpha 1 is there, minus u I will put as v1 cos alpha 1 into 1 plus cd into k. So that's what I'm going to do. I can write v1 cos alpha 1 minus v1 cos alpha 1 by 2 into 1 plus cd into k. Okay, now I'll try to open the bracket. So this will become v1 square into cos square alpha 1 divided by 2 minus, so I'm going to get v1 square cos square alpha 1 by 2 into 2, it is 4, okay, then into 1 plus cd into k. So now what I will do here, actually v1 cos alpha, so it is 1 upon 2 by 1 upon 4, if it is 1 upon 4. So this equation is, I'm going to get as v1 square cos square alpha 1 by 4 into 1 plus cd into k. So this is my maximum generalized, I'm telling, general work done, maximum work done. So where v1 square cos square alpha 1 by 4 into 1 plus cd into k. So now for a D level condition, so for a D level condition, what it is for D level turbine, for ideal condition or for a D level turbine. So what is actually VR1 is equal to VR2, what will happen? Your C is equal to 1. Your beta 1 is equal to beta 2, so your K is equal to 1. So what will happen to your W max? Therefore, your W max equal to V1 square cos square alpha 1 divided by 4, okay, into 1 plus 1 into 1. So it is becomes 2. So 2 by 4. So this will become 2 by 4. I am going to get W max is equal to V1 square into cos square alpha 1 by 2. This is psychological equation number 9. So this is the expression for maximum work done for a impulse case of D level turbine. So this is the generalized one. So whatever I have equation 8 is the generalized maximum work done, or the equation 6 is the generalized equation for any kind of turbine. So here also I can put, here also if you want to put it for an impulse case, I want to find it actually. Cv is equal to 1, your k is equal to 1. So 1 plus 1 it is 2. So this will be 2u into V1 cos alpha 1 minus. So I can write here itself, I can write for a D level case, for a D level turbine. D level turbine. Cv is equal to 1, K is equal to 1, your W is equal to 2 into U into V1 cos alpha 1 minus U. So this is your equation. I can see, I am trying to write a generalized equation, and in that I can take, I can get it for any kind of turbine, what I am trying to use it. So this is the expression for your work done for a single stage impulse turbine. Is that clear? So that you can raise your hand, we can take a further discussion. Before I move to the reaction turbine. Right? Anything you want to discuss? Okay, fine. If there are no questions, we'll move for the next case. So Parsons reaction turbine. I'm just trying to take for a reaction turbine, then I'll go for it. Parsons reaction turbine. See, as I told, Parsons reaction turbine, the degree of reaction is 0.5. And in this condition, what I have is your alpha 1 is equal to beta 2 and your alpha is equal to beta 1. Okay, your flow angle will be equal to your exit, the inlet flow angle will be equal to your exit blade angle, and your exit flow angle will be equal to your inlet blade angle. So this can be proved. It's not a big issue. We can prove it actually, but that's not the case. But for a Parsons turbine, we can this thing will happen. Automatically this will come. So now what we will do is that we'll go with this thing that R is equal to 0.5. Why this particular thing? Alpha 1 is equal to beta 2 and alpha 2 is equal to beta 2. What is the meaning of it? That means I am going to get a symmetrical inlet and exit of the triangle. That means, say if I try to call this as, say, if I call this as A, B, C, and D, and this as D, E, F, okay. So now if you look at it, your triangle ABC and your triangle AEC will be same. So your inlet velocity will same if my degree of reaction is 0.5. That was not the case in case of a D level turbine. Even though we had beta 1 is equal to beta 2, so my velocity triangles were a little bit different. But in this case, for degree of reaction R is equal to 0.5, I will be getting a okay. That's one more thing. The second thing is, you look at the aerofoils. See, your blades, these blades are aerofoil in cross section. But in case of a impulse machine, it was like a cup shape, where your both angles were the same. But in reaction turbine, your blades are of aerofoil cross section. Aerofoil cross section. That's a major difference between an impulse machine and a reaction machine. So this is the one point. Okay. Now, construction wise, I am trying to take a single stage reaction machine. That is, it has a stator, it has a rotor. Now, in case of a reaction machine, what will happen? Both your pressure energy as well as your kinetic energy gets absorbed. But in case of an impulse machine, only the kinetic energy gets absorbed, your pressure energy remains constant. Now, if you look at the your pressure and velocity, how those things are changing. So now I do have the inlet pressure, it enters at some inlet pressure, and there is a drop in the pressure, that is when the steam is expanding, that is when the velocity is increasing. Look at this, when the velocity is increasing, this is my velocity, okay, this is my pressure. So pressure is dropping and the velocity is increasing in the nozzle. When you come to the rotor, both pressure and kinetic, that is your velocity, both are dropping. That means there is expansion of pressure, that is pressure is dropping, velocity is also dropping. That means energy is not only from absorbed, maybe conversion of kinetic energy, there is energy also drop. The energy conversion is because of the drop in pressure energy also. But in case of a Turbines turbine, it is 50%. So 50% of kinetic energy, 50% of your pressure energy. Okay, that's why R is equal to 0.5. Yes. And as I told, in case of a Parsons turbine, your alpha 1 is equal to beta 2. The flow angle is equal to exit and your flow angle at the exit is equal to inlet. So that will lead to what is called as symmetrical triangles. This we will get a symmetrical triangle at inlet and exit. Now, expression for work done. So it's a little bit, it's the same actually. Expression for the work done. So now, I'm trying to take the same velocity triangle, what I wrote, same velocity triangle. Here, Euler's expression, it is VW1 minus VW2 into U. So it becomes VW1 plus VW2. Okay. Now, from the velocity triangles, both at the inlet and exit, if I try to take cos alpha 1, what is cos alpha 1? It is VW1 divided by V1, so that I is equal to V1 cos alpha 1. What is my cos alpha 2? 2 is equal to VW2 by V2, so VW2 is equal to V2 cos alpha 2. Or I can write, what is cos beta 2? Cos beta 2 is equal to VW2, so same thing. So it is VW2 plus U divided by VR2, or I can write, okay, VW2 is equal to, or I can write this, I can write VW2 is equal to V2 cos beta 2 minus U. So let me call this as expression number 4. Okay. Now, you substitute this 2, 4 and 1 in equation 1. So if you substitute VW1 and VW2, same expression. So substitute for VW1 and VW2 in equation 1. If I do that, your VW1 is equal to V1 cos alpha and your VW2 is equal to VR2 cos beta 2 minus U. Okay. So your expression W will be equal to, or W is equal to V1 cos alpha 1 plus cos beta 2 minus U into U. Okay. Let me call this as equation number. See, as I told, for a R is equal to 0.5, that is, for a condition R is equal to 0.5, your VR1 is equal to, or VR2 is equal to, VR2 is equal to T1, and your alpha 1 is equal to beta 2. Why it is so? Because symmetric triangle. Look at this particular thing. Now, if you look at this velocity triangle, if I tell my alpha 1 is equal to beta 2, so if you go see here, if my alpha 1 is equal to beta 2, what happens? Your VR2 is equal to VR1 because of the symmetry in triangles. For R is equal to 0.5, your alpha 1 is equal to beta 2, your VR2 is equal to V. So my expression I can write. So because of this condition, the equation 5 I can write it as your W is equal to V1 cos alpha 1 and VR2 I can write it as, so I can write it as V1 beta 2 I can write it as 1. So I can write it as V1 cos alpha 1 minus 2 into U. Or let me write this as V1 cos alpha 2 V1 cos alpha 1 minus U into U. Okay, or I can write, either I can write in terms of alpha 1. In some textbooks I can write as they are writing this particular thing, W is equal to 2 V1 alpha 1, I can write it as 2 minus U into U. Perfect. Either alpha 1 or in terms of beta 2. So both are correct. The way I can write. So this I am calling it as expression number 6. Okay. Now I am going to define one what is called as speed ratio. So let's define speed ratio. Let us define a speed ratio which is called as phi. What is actually the ratio of your blade speed to your flow velocity at the inlet. Flow velocity at the inlet. What is it? V1. So U by V1 is called as phi. Okay, I'm going to write phi is equal to U by V1. I'm going to write your velocity, that is your speed ratio in terms of U by V1. Now if you go and see here, actually, if you go on this particular expression, so I'm going to take the equation number 6, I can modify this. Your W is equal to, so W is equal to, if I try to take my V1 square outside, if I try to modify this, if I try to take V1 square outside, I can write this as 2 into cos alpha 1 into U by V1 minus, so V1 square, I'm taking it outside, this will become U square by V1 square. Just I'm modifying the equation number, taking my V1 square outside. I can write it as 2 into cos alpha 1 into U by V1 minus U square by V1 square. So now I'm substitute for U by V1 as 5. I can write it as W is equal to V1 square into 2 into cos alpha 1 into 5 minus 5 square. Suppose instead of alpha 1, I can write the same expression in terms of beta also, or I can write the same expression, W is equal to V1 square 2 cos beta 1 into 5 minus 5 square. I can write in terms of alpha or in terms of beta. So I'm going to call this as expression number 7. As I told, this particular whatever I have, no, this is your W. So this is your W, what I call W, the work done in your reaction machine. Now this is in terms of blade speed, or we call it as speed, which is phi. So if you look at it, actually we have your V1 square to, or kinetic energy of your particular blade will be fixed. The kinetic energy available at the moving blade will be with respect to relative velocity. Okay, the kinetic energy of the fixed blade will be only with respect to your V1, but kinetic energy of the moving blade is with respect to relative velocity. Now, when you have this particular kind of relationship, your stage enthalpies are going to change. The stage enthalpies are going to change, and that will have an impact on your efficiency. Okay, so if you look at only the work done, so this is the expression what we have. But that particular thing is very much important, because your blade efficiency has a lot of impact based on your what you call it, zero velocity as well as range velocity. So those points we will discuss. Then we will go for multi-staging in the next class. Okay.